Oops, man. All right. So the radiation detection instruments, there's definitely different types for sure. The types that track sort of in a live way that are, like battery operated, can track you right now, they're going to have really 3 different ways of doing that. Okay, 3 different ways of detecting radiation. Now, we already mentioned, how is radiation detected?
Bless you. Thank you.
Bless you. What are we measuring? What are we looking for?
Exposure.
Right, which is what?
Intensity.
Intensity of radiation above the surface of the object, right? And so what are you measuring? Is your detector measuring an amount of radiation? Or is it measuring something else and inferring the amount of radiation? Of the air, right, in the room, right? It's measuring ionization events, which generates an amount of electric current. The little computers read the electric current and infer amounts of radiation from that, right? Okay, so there's 3 ways that these devices are going to be able to do that, right? You've got pulse detection, okay, which is just detecting single events, right? Think of those as like clicks on a Geiger counter, okay? Everyone's seen a movie sometime that had a Geiger counter, they waved it around some radiation area and it was clicking away, right? And you probably in those movies, if they used a Geiger counter, it was clicking, 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 and then went crazy bananas when they went over like one specific spot, right? Started to click all crazy, okay? That's a pulse detection method where it's basically every ionization event gets detected, generates a small current. That current tells the machine sound an alarm, which is in the form of a click. Okay, so every time that thing clicks, that's representing a detection of a single event, a single ionization event. And that's like what we think about being done on a Geiger counter. The rate detection mode doesn't just count the number of clicks that happen, the number of decay events, the number of radioactivity events. This adds them up, right? This is telling you how many are happening per hour, right? So it's giving you a rate, but not for, and you don't have to run it for an hour, right? You turn it on, and immediately it's going to tell you what's your rate, okay? It's going to tell you the decay, the radioactivity rate. Integration mode. Oh, hang on. Before it decides to shut down on me. Okay. Integration mode will just simply add up all of the clicks over time, okay? And give you not the rate per hour, the amount per hour, but just a total quantity. Turn it on for a minute, it'll tell you how much exposure happened in that minute of time. That's integration mode, okay? And then the next thing to learn is there's going to be, these are the characteristics of our detection devices, okay? So these 4 things will determine how well the device does what it does, okay? The first characteristic of any detection device is sensitivity, okay? A more sensitive device is able to detect smaller amounts of radiation. A device that is not very sensitive could tell you, is there radiation or is there not, right? A very sensitive device would tell you exactly how much radiation down to very small quantities and very precisely, okay? The way you get more sensitivity is by having larger gas chambers, okay? So now's a decent time to just bring out the Geiger counter so you can see what they look like. This is our old one, no longer functioning, but still shows you the device. All the computation and displays here, but this is the sort of the business end of it, okay? Inside of this, so under this, is a chamber packed with gas, okay? This chamber inside of here is called a Geiger-Müller tube, okay? Geiger-Müller tube. It's a little chamber full of gas molecules, okay? And these gas molecules, when radiation strikes them, the gas molecules get ionized. Small electric current travels down this line to the detector, and the detector clicks, okay? Now, this has a relatively large ion chamber. I mean, you can see the size of this cylinder here. It's relatively large. Compared to the current Geiger counter that I have, which, I mean, the counter itself, right, is about twice the size of the ion chambers. The ion chamber can't be very big inside of here, okay? This has a much smaller chamber, a detection chamber, okay? This device, much more sensitive than this one, okay? Because of the size of the detection chamber. In here somewhere is going to be a small little detection chamber, probably about the size of this pen cap, okay? Stuffed somewhere in here along with the electronics, okay? So larger detection chambers equal more sensitive detectors. Associated with sensitivity is accuracy, right? Being able to accurately report a number, not just be able to report if it's a very small or a very large number, but be able to report it in an accurate way. Precision of the measurement. Number 3 is resolving time. It's the time that it takes for the machine to basically reset, okay? You know, if your machine can only detect 1 decay event per second, but your radioactive source has 2 decay events happening per second, then you can't detect the 2 events. The detector's only going to tell you 1 event per second, 1 decay event per second, 60 events per minute, right? Where it's really happening at a rate of 120 events per minute. That's resolving time. It takes time between each detection for the device to sort of reset and expect the next event, okay? Machines that have devices that have a very short resolving time can achieve greater accuracy. So it's the amount of time it takes for the device to reset and then detect the next event. Lastly, range. Matching of the instrument's design and sensitivity to the type of radiation, right? These are sensitive to a range of energies, and so it's not how far you can be. We're not talking about how far you are from the source, not that kind of range. We're talking about the range of energies that the device is designed to detect, okay? Devices that are designed to detect a very specific type of energy, like if it's only designed to detect alpha particles, it's going to be really, really great at detecting alpha particles. It's going to have high accuracy, high sensitivity for detecting alpha radiation, but you expose it to X-rays, and it's going to have very low sensitivity and very low accuracy for that. That's the point about range, okay? If a device is made to detect a wide range of energies, then it's going to be good at detecting lots of different things, but it's probably going to be less accurate. You get the idea, right? Like this is really good at detecting a wide range of energies, but because of that, it sacrifices some accuracy, right? Something that was very specifically designed to detect a specific kind of energy can be much more accurate at that than something that's designed at detecting a wide range of energies.
And then we go a step further and make sensors that are based on the science, but their sensors not a counter per se. So like if you're in a power plant, radioactive power plant, they'll have sensors around
that are specific to the types of energies that power plant will emit. Yeah, so that's what we think about with range, right? There's all different levels of energy that radiation can come in. Okay, you can get different amounts of energy with different types of radiation, and the range is basically saying I'm either designed to detect a wide range of energies or a very narrow range of energies. And roughly speaking, the more types of radiation a device can detect, the less accurate the device becomes. That's the idea. Okay, so let's now take a look at some of our different types of detectors. Okay, now we're going to run through these different types. This is the Geiger-Müller tube type of detector that I've shown you, that I brought out here. But we're going to look at a couple different types, including the type that you guys wear on your lapel. You know, your dosimeters. Those are types of detectors. So first off, scintillation detectors. Right? You guys learned about scintillation last module in the context of your image receptors, right? Some types of image receptors use scintillation to, when they're struck by X-rays, convert X-rays to visible light and use the visible light to expose the image receptor. This is the same idea, okay? Scintillating, a scintillation screen is a screen of material that when it's struck by some type of radiation will emit a different type of radiation. Okay, this is the emission of light, or fluorescence in this case. So what you have is you have a scintillating detector, a detector that when it's struck by radiation, it emits light. This detector will be made of something like sodium iodide or cesium iodide. Don't worry too much about the materials themselves. Coupled to a photomultiplier tube. A photomultiplier tube simply amplifies the energy, amplifies the electric current. I'll show you a picture in a second. Let me read here. Light from the crystal. The light came out of the crystal because it was struck by some radiation. So light comes out of a fluorescing crystal when it's struck by radiation and strikes a photocathode. A photocathode is a device that when struck by light emits electrons. Photocathode, which emits electrons by the photoelectric effect. Electrons are then accelerated and multiplied by a series of dinodes to amplify the electrical pulse. And it looks like this. So from left to right on the screen, you have your fluorescent crystal in here, okay? So radiation comes in from that end, okay? Strikes that detector, causes that detector to emit light rays, okay? Those light rays travel to the photocathode. The photocathode emits these electrons, okay? Those electrons are now electric current. Electrons freed up to move through the circuitry, and those electrons are bounced back and forth, amplifying them, okay? These things are called the dinodes. Basically, just bounce the electron stream back and forth. Each time it gets amplified a little bit, and what comes out that end is electric current. Okay, so what comes in this end is an amount of radiation, and out that end is an amount of electric current, and we can infer from the amount of electric current how much radiation came in that end. Okay, scintillating detector. The next type of detector are called OSL detectors. Optically stimulated luminescence detectors. These are what you guys, so these are one of the options for dosimetry badges. These are kind of like, if you guys remember from the previous digital module about the CR cassettes that had a photostimulable phosphor. When X-rays strike them, it stores the X-ray energy until you can take the processor, or take the cassette to the processor, right? It's the same idea here, okay? So, special materials, quartz or feldspar crystals. Again, don't worry too much about that. Special materials, when struck by X-rays, will hang on to the energy, right? So X-rays are a form of radiation, radiation's energy. So X-rays strike these special materials. The materials hang on to the stored energy from the X-ray beam and then re-emit the energy as visible light when stimulated, okay? The way to stimulate them is to shine a special light on them, such as a special laser, okay? This is all done in a very controlled setting. If this sounds familiar, as I just said, this is the same process for the photostimulable phosphor plates used in computed radiography, CR cassettes. So if you know about OSL detectors, you'll know about CR cassettes. Upon the X-ray exposure, the ejected electrons are captured and stored in electron traps within the crystalline structure of the material for later re-emission at the laboratory when we send these back to the company. So a badge like this might have a special crystal in it, quartz or feldspar crystal, again, it doesn't matter, right? But a special crystal in it. Every time some X-ray photons strike the detector, they get captured, okay? This badge goes back to the badge company. The badge company puts this into a special light, or underneath a special light with a special detector. The light shines on this, causes this device to re-emit all of what it had stored up. Their detectors capture the light that it emits, read how much light was emitted, okay, and give you an amount of dose, to tell you what your dose is based on the amount of stored energy this thing captures, okay? OSL, optically stimulated luminescence, just does this by using optical light, visible light, back at the laboratory to stimulate these, to re-stimulate these. The other option is called thermoluminescent dosimetry. Okay, so thermoluminescent dosimeters, which these are actually TLDs, thermoluminescent dosimeters, are the exact same thing. Okay, so optically stimulated luminescence dosimeters, OSL badges, and thermoluminescent dosimeters, TLD badges, are the same thing. Okay, let me explain how they're a little different, but they're exactly the same. OSL badges, let me backtrack for just a moment. OSL badges have a crystal structure, again, quartz or whatever, doesn't matter, but a crystal structure, material in here, that when X-rays strike them, they capture the electrons in these electron traps, okay? The electrons store the energy from the X-ray beam, and that stored energy stays in here until you get to the badge company. You send this back, the badge company puts it into their special machine. Their special machine will shine visible light at the device, at this, okay? When visible light hits these atoms, the atoms will cause the electron to jump back into place, re-emitting the light that it stored, re-emitting all the energy that it stored, okay? Optically stimulating this to luminesce, okay? To shine light, luminesce. Now, TLD badges do the same thing, okay? The TLD badges have the similar material, stored energy from the X-ray beam is captured, goes back to the badge company, they put it into their special machine, but this time, instead of, as with the OSL badges, they would use visible light to stimulate them, with the TLD badges, they use infrared light, heat. You can't see infrared, so we call it heat. You can feel it, right? So TLD badges are stimulated back at the badge company by heat. OSL badges are stimulated by light. And they say what they're stimulated by, right? Thermoluminescing dosimeters, well, they luminesce when you put some thermos on them, right? Thermoluminescing, right? When you put heat thermo into them, they luminesce, okay? They shine light. They shine the light that they had absorbed. And by the way, right, more light emitted from the thing at the detection company means more exposure, right? If this thing shines strictly no light out of it, well, then there was strictly no exposure. This will always have something, by the way, because remember we talked about natural background radiation? So it'll always have something. The more exposure this receives, the brighter this thing will shine, and the more their little detectors at the badge company, the more their detectors will pick up the light being emitted. More light gets emitted from this under conditions of high exposure, and less light under conditions of low exposure. Anyway, though, TLD badges, which are this type, and OSL badges, which I'll show you in a second, they use the same principles. They're just sensitive to different wavelengths of light. So let me show you what OSL badges look like. If your badge looks like a hexagon, it is going to almost always be an OSL badge, okay? So they're shaped so we can sort of visually identify them as such. OSL badges are the most expensive, but they're also the most accurate. TLD badges follow very closely behind, and they're almost always going to be rectangular square. Okay, they do exactly the same thing. Okay, just a difference in when it gets back to the laboratory, how they are, you know, how they read the energy from them. That's the idea. Okay, so let me just bring up the TLD section so you can read that. So thermoluminescent dosimeters, right? Just a different crystal this time. Lithium fluoride does the same thing, stores the energy and delays the emission of light until they are stimulated. In this case, just by heat. Okay. Now, when you look at your dosimeters, you'll notice that like it's not like a blank face. Like there's writing on the face for one, but then you'll see like the little what looks like metal pieces here, a little bubble thing over here. Okay, these are filters. Okay, so there are small pieces of material put into your badges. Even if you can't see them, there's small pieces of material put into the badges that act as filters. Okay, there's materials that act as simulated bone, aluminum, tin, copper, or areas with no filter at all, okay? And that way now they can tell, you know, if there's exposure behind the aluminum part, they can tell you got more exposure in high energies, because if it takes higher energy to penetrate the aluminum, okay? So they can tell your relative exposure to different body areas based on how much exposure was received by each part of the actual square, right? Because each part on this square will have different filters in front of it, okay? And these are worn like this, facing forward, okay? So different filters will allow different amounts of penetration in different spots. So here's showing you, these arrows are showing you placement of the filters. For example, if we zoom in on this one, this is a pretty good example, right? Showing you things like copper, probably aluminum, maybe simulated bone, maybe no filter, right? And now when this closes, those filters will sit in front of specific spots on here. And when this detector material gets back to the laboratory, right, they stick it in their oven, they can read how much light is being emitted from each of those spots behind where each of the filters were at. And then they can tell how much radiation you got deep down in your body, how much radiation you got at the surface of your skin, and at what energy levels that radiation came in at, okay? So thermoluminescing and OSL badges do a very similar thing. The other type of detecting badge, I have it on here. It's called a film badge, okay? Which they'll look exactly like this. They'll look square or rectangular. But they'll be inside of here, instead of a special crystal material, it'll be a piece of photographic film, okay? The upside to these are film badges. They're way cheaper, very, very cheap to buy, okay? So if a company's trying to save money, film badges are great. The downside to them is, you know, these can track for 3 or 4 months. They're usually quarterly, so 3 months, okay? 90 days or so, where the film badges, they can only track for about a month, okay? So while they're significantly cheaper, you also have to purchase more of them. They still come out to be cheaper, right? But you have to purchase more of them more often, so 12 in a year rather than 4 of these in a year, okay? But the other thing is that they're much more sensitive to like the environment around them, to heat and moisture, and you know, just radiation around them. I mean, if you put this accidentally through your washer and dryer, it's probably not going to be a big deal. Don't do that, but it's probably not going to be a big deal, right? Same thing with your OSL badge. But if you put your film badge through the washer and dryer, it's going to destroy it, okay? They just can't handle the harsh environments, okay? So they're an option though, okay? They have a literal piece of chemical film in them, and with similar like filters in front of them, okay? And the film becomes fogged with increasing exposure. So there's a way to read, oh, they have it on here, good. There's a way to read the amount of exposure with a special device called a densitometer, okay? A densitometer, they would take the film out of here in a special way, and the densitometer basically clamps around the film and can measure how dense the film is. The film gets denser, more fog, with more exposure, okay? And they can measure that relative density with a densitometer. So they need an extra piece of equipment, but it's a way to do it. And again, the downside is, everything I just said is on this slide here. The downside is that they're just very, very sensitive to their outside environment. And notice accuracy for TLD and OSL badges. They're accurate to plus or minus about 5 millirad, 50 micro rem, or 50 micro gray, or microsievert, excuse me. So they're sensitive to very small amounts, where the film badges are less sensitive. You'll have more of a variance in the readout. Okay, but they're cheaper. That's the important thing. All right. So you guys, as radiographers, X-ray technicians, are monitored with either OSL badges, TLD badges, or film badges. All 3 are worn at the lapel level, outside of any aprons, any lead aprons. And the same thing will also be used as the fetal dose badge too, that's worn underneath the lead apron in pregnant radiographers. They just wear it down. Second badge worn down, usually at the waist level, behind any lead shielding. Okay. Now, but what if you're somebody who works with radioactive materials, right? If you're like a nuclear medicine technician, you are handling radioactive materials. In that video, they showed you that big metal syringe, right, that they were using for nuclear medicine, and it was in a special carry case, right? somebody who's working with that, they need to be monitored much more regularly rather than every 3 months. We need to monitor them right now. Okay, so they'll wear things like dosimetry rings, okay, that can actually measure because their hands are working near the material. They'll wear dosimetry rings. They will also use things like gas-filled pocket dosimeters, which looks like a pen, okay, and it's a dosimeter that can read in real time amounts of exposure. So let's take a look at how that might work. These gas-filled detectors work by having a chamber filled with gas, okay. And what the special design of these chambers are, the chamber is full of a special gas. This gas is just, it's kind of like the air, just easier to ionize, okay? You know, the air is hard to ionize, put a special gas in there that's like ready to go. Usually noble gases can do this very well. Helium is an example, probably not a good example for this, but noble gases put in there. Okay, so chamber filled with gas. And what the device will do is it'll run in a negative electric charge around the walls of the chamber, okay? And you've learned that opposite charges attract and like charges repel, okay? So when some radiation strikes the chamber, the gas inside of the chamber frees up some electrons, okay? Those electrons are pushed away from the walls of the chamber, and running down the middle of the chamber is a metal pin called an anode pin. That metal pin, they've run a positive electric charge through that pin, okay? Negative charges are attracted to positive charges. Electrons have a negative charge. So, you liberate some electrons, they're attracted towards the anode pin, and when they strike the anode pin, you get an amount of electric current running up the pin. That anode pin runs to the detecting device and you can measure an amount of radiation with that. That is one way these gas chambers will work if they're electronic, okay? Now specifically these pocket dosimeters work in a slightly different way, okay? So let me show you how these pocket dosimeters do what they do. Now, the pocket dosimeter will be a pen like this, and at the top of the pen there's a window that you can look in, okay? So right where the pen would clip on, there's a window up here. So in this picture, they're showing you an eyeball looking at that window. Okay, so at the beginning of the day, well, what you've got in here, let me restart this. What you've got in here is you've got an ion chamber, a chamber. This time with the pocket dosimeter, no pin running down the middle. Okay, what they have is they've got basically a foil leaf. Okay, it's a material that's very thin and can, with difference in charge, can be pushed around. Okay. Positive charge running on the walls, positive charge to the walls of the chamber, positive charge to the pin. Positive charge repels a metal foil leaf from the chamber wall. As electrons are freed from ionizations of the air, the charge is neutralized. Okay? The leaf moves closer to the wall. The leaf moves up that way, or down that way, it doesn't matter, but the leaf moves, right, with increasing charge. Okay? And on here, on the screen, or on the face of this, which you're looking down on, you can see the cross section of the foil leaf, okay? That's just, in this case, it's shown as a green line. And you can see your graduated marking showing you indicating amounts of exposure. As this foil leaf moves from no exposure at the beginning of your day, as you add on exposure, this foil leaf will continue to shift and shift and shift and shift over, moving over and over and over. So from this view, like that, you're looking down on it, you can see your little foil leaf moving over and over and over, reading increasing exposure throughout your day, okay? At the end of the day, you take out your little pocket dosimeter, you look at it, you note the reading, 75 milligray. By the way, 75 milligray, have they passed any limits in one day? What limit did they?
50.
Yeah, they passed their 50 millisievert, because 75 milligray, if it's X-rays, it's 50, right? It's 75 millisieverts. So they've passed their yearly prospective limit. They've also passed their retrospective quarterly limit. And they could potentially have gone above their lifetime limit, right? We don't know what their lifetime exposure was right now. We don't know how old this person is, what their life, but they passed, importantly, the retrospective quarterly limit and the prospective yearly limit by the 75 milligray. So this person needs to take it easy, right? Take it down a notch. Step away from the radioactive material.
Do some paperwork.
Go do some paperwork, right?
Time, buddy.
So that's the idea though, right? You take it, you look at it periodically, you remember your dose, you just go back up to your work. At the end of the day, you'll take your pen out, you will, on your log, you will log your dose for the day. So someone has to write this down. The person using the pen has to write this down and keep track of it for themselves. And you'll write it down, and then what you'll do is you'll stick it into a discharge device. So down at the bottom here, charging contact, you'll basically plug it into something and it'll discharge everything that it had absorbed, and it'll basically be reset for the next day. Next day you come in, stick it in your pocket, starts at 0, and then throughout your day it begins to read dose, okay? And so that's one way that somebody can track, you know, over short periods of time what their exposures are if they're around high levels of radiation. Pocket dosimetry. Okay, the next thing we're going to get into are our Geiger counters, our more types of gas-filled detectors, okay? So our Geiger counters are going to work like what I just explained a minute ago, right? You've got a chamber full of special gas. Chamber runs a negative charge along the walls and a positive charge along a central pin down the middle of the chamber. So that's exactly what these have, okay? A chamber, negative charge on the walls, little anode pin in the middle somewhere in the chamber. That anode pin will be struck by freed electrons and generate some current. The current will run on the screen here from left to right, up the anode pin, out the wiring, through an electronic amplifier, just to make the signal bigger, okay? And then give you a readout on your screen in real time. One electron released from the gas chamber, in the gas chamber, reaches the anode pin for each X-ray ionization event. Each one of those can be amplified and detected as a click, okay? Or an alpha particle or beta particle, whatever, but each time it can detect a decay event, a radioactive event. Okay, so Geiger-Müller tubes, these type. High sensitivity, low accuracy, and narrow range. So very sensitive, hard to report accurately. This will tell you if there's radiation, any amount, high or low amounts, but they can't tell you exactly how much there is. They're less good at that. And they have a narrower range for detection. So that they have downsides. They are good. They're great instruments for environmental radiation surveys or checking contaminated surfaces in like nuclear medicine or other laboratories. And we can actually, because we're exposed to natural background all the time, when we turn this on, I can't make it louder, but I can make it sit here. Every time that clicks will be one decay event detected. So and right now it's on a couple of different modes. I know it's a long way away from you guys right now, but the big part on the screen here is giving you counts per minute, okay? So far, just sitting here, this thing has detected 6 clicks, 6 decay events, okay? And it doesn't matter where I put this in the room, it will detect at the same rate, right? Unless one of you is carrying like some uranium-238 in your pocket or something like that, right? It's gonna detect things at the same rate, okay? What's it detecting right now? I mean, it's detecting radiation, but what kind? Where's this radiation coming from? Not the lights in the room. I mean, the lights in the room emit visible light, but that doesn't ionize anything. Ourselves. My computer.
It's warm.
My natural background, right? Just the fact that we're here on Earth, right? We're getting radiation from the sun, the stars, other places, right? Our own atmosphere, our own bodies, our Earth, the ground, right? And that's what it's detecting. It's detecting our natural background right now. Okay, so this is just always going to be around. You take this outside, set it outside in the sun. It's going to do the same thing as it is right here. Okay, it's going to detect natural background continuously. So I'll just let this sit and run. Good. So these are our Geiger-Müller tubes. Again, this is the same thing. Okay, so right now, three measurements it's displaying for us. It's displaying our counts per minute, just giving us a total number of decay events that it's detected in the amount of time that it's been running. Okay, so right now it's up to 23 counts per minute. I think typically it's like 27, 29 counts per minute. Below that, and given in smaller writing, it's giving, I have to look at this, it's giving me my microsievert per hour. Okay, so right now we're at 0.16, so 1/10 roughly of a microsievert per hour. And it's converting that into rem as well, or sorry, rad as well, right? No, rem, excuse me, rem, 0.018 micro rem per hour. Sorry, millirem per hour. But anyways, it's giving me both. It's giving me the standard unit and the SI units, the British and SI units of measurement, all there, plus our counts per minute. You can ask these things to just count in pulse mode like this. You can ask these things to give you the rate, which this is giving us both. It's giving us the rate per hour, and it's giving us how many per minute, which are just the counts, the clicks. But you can also ask these things to integrate, to add up. You know, put it by next to a radioactive source. It has settings for this. You can put it next to a radioactive source and tell it, measure this radioactive source for 5 minutes and give me the total amount of radiation emitted by the source over 5 minutes. I've done this with bananas, and it's the same as our natural background. Okay, the bananas emit the same amount of radiation as the natural background. But there you are. So Geiger-Müller tubes use a special gas. I keep saying this gas is special. Here's why it's special. Let me come over to the periodic table here for a moment. You guys will get used to this back again when we get through radiation safety. We'll get back into physics. If you're still with me, you'll get very familiar with the periodic table of the elements. It's set up in a specific way. Okay, so these aren't arbitrarily placed on here. One way that this is set up is by columns. Okay, the columns are indicating to you how full the outer shell of electrons in the atom are. If an atom has a completely filled outer shell, we say that the atom does not necessarily like to interact with other atoms. Okay? Atoms with completely filled outer shells are listed over here on the right-hand side and are shown in this blue color. Okay? They are called noble gases. You guys probably all remember that from science class, noble gases. And what that means is, think about like nobility, right? They're not going to interact with a bunch of regular people, right? That's the idea, right? Noble gases don't interact with all the other atoms because they don't need to. They have everything they need, okay? Atoms interact with each other and form chemical reactions when they need to borrow or share or exchange electrons, okay? That's what chemistry basically is, right? Is the interaction of atoms gaining, giving, or sharing electrons with each other, right? Atoms that don't need to give, gain, or share electrons, they don't tend to interact with other atoms. We call them noble gases. And they stay as a gas because they don't interact and form solids with other materials. So they're a gas. Helium is a good example of that, okay? Helium has an atomic number of 2 protons in the nucleus, 2 electrons orbiting around it. Helium's full, okay? Neon, atomic number of 10. It has 2 electron shells. The inner electron shell has 2 electrons. The outer electron shell has 8. 8 is the maximum number of electrons an outer shell of an atom can hold. Okay, so neon is full. Same with argon, same with krypton, same with xenon and radon. Okay, notice they're different. Like helium only has 2 protons in its nucleus, where radon has 86 protons in its nucleus. Radon is significantly larger, but these all will chemically act very similar to each other, okay? Specifically, they don't interact with anything else, right? So argon here, number 18, is one of these noble gases. Oh, and the other thing I was trying to get to, their outer shells are full, right? So if you ionize them, if you put energy into the atom, the electrons have nowhere to go, right? Their shells are all full. So take like argon, for example. The inner shell of argon, where there's going to be only 2 little electrons floating around, if you struck one of those electrons with an X-ray photon and it wants to jump up to a higher energy level, it can't fit into any of those energy levels without shooting off an electron from the outer level, from the outer shells. Okay, these atoms are easier to ionize. In other words, okay, noble gases become easier to ionize because they're already full. So argon is a good example of that. Okay, so argon's injected into these ionization chambers because it's more readily ionizable than room air. Room air is mostly nitrogen, also oxygen. Harder to ionize because oxygen and nitrogen are not noble gases. Okay. Single events heard as a click or beep. And They say usually cannot be operated in integrate mode. They can integrate just fine. Most of the newer ones. Sorry, hang on. So let's see where the ones that we mostly deal with. Let's give some advantage disadvantage to them. All right, so we've learned a little bit about Geiger-Muller tubes. We don't focus a bunch on these because we don't actually use our Geiger-Muller tubes in the X room. The only reason I have these are to demonstrate, show you, so you can see, you know, sort of how they work. And the coolest thing for me, right, is that they're detecting right now, right? It's detecting real radioactive events happening right now in the room, and not over there by you guys in the back. These radioactive events are happening right here, okay? If I go put it back there, it's going to detect your events, right? But they're going to be the same. That's what's kind of cool, right? Okay, anyways, personnel monitoring devices, right? OSL, optically stimulated luminescence detectors, or thermoluminescence detectors, have the same basic idea behind them. They're highly resilient, very accurate, have long use periods, slightly higher cost is the disadvantage. Film badges, highly susceptible to things like heat and fumes and moisture. And so that's, look at their advantage is that they're susceptible to heat and fumes and moisture. Their advantage is a disadvantage, okay? They are just not the best way to do things, okay? You know, I don't even know why they put that here. The only advantage that I see to a film badge is cost, right? From an administrative standpoint, it's just cost, right? You're going to go through more of them, but as long as they're significantly cheaper, then it becomes an advantage. But susceptibility is not, from my point of view, an advantage. Their disadvantage, the main one, is short use periods. 1 month is a short period of time. Months pass very, very quickly, right? Quicker than you think they do. And so all of a sudden your badge is expired and you got to make sure you switch out for a new one, which means every month someone's got to be checking this, right? So every 4 weeks someone's got to be getting new badges in, switching out the old ones, sending them to the laboratory for measurement. This is going to happen a lot more frequently than the 3-month versus 3-month time frame for OSL TLDs. Pocket dosimeters, the advantage is immediate readout. You get to know right now if you're being exposed to radiation. The disadvantage is they're not very accurate, right? You saw those, I mean, if you go, let's go back briefly and you can see exactly how not accurate they are, right? Remember, graduated markings are all you have to make your measurements off of, right? Like on a tape measure, right? If you have a tape measure that only measures in inches, well then something is either 1 inch or 2 inches, right? You can't measure anything to 1.5 inches if you don't have a tape measure that measures in 1/2 inch increments, okay? This thing, as shown here, only measures in 50 milligray increments, right? Now, you can infer that this is 75 milligray, but you have no graduated marking to tell you that, okay? You have a graduated marking at 50 and a graduated marking at 100. They're less accurate for these exact reasons, okay? And this little foil leaf, there's going to be some wiggle room. It's going to move more or less, it can receive the same amount of radiation and move more or less on different days, right? With different heat and pressure in the room. There's a bunch of factors that are going to go into making this thing less accurate than other ways of measuring. But again, the main advantage is immediate readout. So again, if you are maybe an interventional radiologist, maybe you're a nuclear medicine technician, maybe you're a radiation physicist working around radioactive materials, then this is going to become very useful for you. The next thing to know is all personnel monitoring, oh hey, I gotta stop. All personnel monitoring badges are sensitive to background radiation, okay? For that reason, a control monitor needs to be kept around, okay? So in this big box, I'm not necessarily gonna go hunting for it, but I see it, yay, I got one. So in this box is a badge labeled control, and it says right on it, do not wear, okay? This badge will be shipped in the box with all the other badges. It will not be dispensed to an employee or a student, and it will stay in this box. And when we send these badges back to the company, this badge will have some radiation on it, okay, from natural background. So what they'll do is, shoot, hang tight. I'm gonna go get another towel. I'm just trying to keep this from getting to my computer for a second. Okay, mischief has been managed, so give me 2 seconds.
What'd you learn from that?
This is why you don't keep liquids next to all your important electronics. Okay. So the point is, as I finish cleaning this up, your badges come with a control. That control is subtracted. The dose that control badge receives is subtracted from yours. So your badge receives background radiation plus whatever you get occupationally, and they just subtract away the natural background from you. Okay. The control badge has to be used for that. I don't even know where my control badge went. I tossed it. Good. So this should stay in the pouch. Make sure it says make sure you note that it says "do not wear" on it, and never wear it. There may also be an additional badge put in here. Schools like ours have to have them. Let's see if I can find it. No, that's fine. In here somewhere will be a badge. Every quarter when I get my new badges, it'll be labeled monitor. Okay. That monitor badge can be placed around the facility in different rooms at different times, rooms adjacent to the X-ray room, and you've guessed it by now, do exactly that. Monitor the amount of radiation that might be considered leakage radiation from the room. Okay. So that's how these personnel monitoring badges work. Basically, they just take away the natural background and give you what you actually received occupationally. With that,